Well, rather than continue to wait, I have some preliminary words that I'm going. I think he's on his way, but preliminary words that I wanted to do here. So many years ago, you can pay attention here now. Many years ago, we ventured to a place called Gondar. It's not in Middle Earth, and it was not in 2000. Ethiopian time is different. They're 8 years behind. So we go 8 years younger. So who was traveling? A much younger Mike than me. I had less hair and less weight at the time. Yeah, well, it's I had just been in a cramped vehicle for a very long time, and I didn't want to slip off the back of the hill slope there. We met this young man, Wubitz. That's Gabriel Sinai. Brian, right here in front. We have some. And he gave us a tour of the University of Gondar, where he was teaching GIS. Here's a state-of-the-art computer laboratory in 2009. Notice the cathode ray tube monitors. Not that long ago, things were done very differently. There's I don't know if this is the GIS or the image processing lab, but you know, no air conditioning, so you got to keep things cool in there through shades. So we convinced Wubit to join the program here in 2011. He arrived, and after a year, what a transformation. A little bit more weight there, a little bit different hairstyle. So one of the questions, you know, is really, what happens in Ethiopia when we go to Ethiopia? This was earlier this year. Wubit is practicing taking a selfie. At the same time, Mike is outstanding in his field. One of the things that we do a lot of road trips to check things out. And when you come across something like this, we have to stop because Mike has to go check this out. And he gets up close and personal. Wubit's a little concerned that he might fall in. I look at this and I think, you know, is this kind of like Narcissus? But he really, as he's standing there, people from around the area walking by on the road is like, what is this guy doing? What is this Ferengi staring into this pool for? And this is the kind of pool that you get. You see the dragonfly there. That's quite nice. But the water quality is kind of nasty. And of course, this is one of the things that is of interest is this a breeding spot for malaria mosquitoes. These are actively used water sites. Just a few minutes later, here's someone filling up his water bucket from these sites. So all of this is kind of give you a context to go to something completely different, which is what Wubit is going to be talking about. And we will exit from here and bring up the next one. So that would be this one. Now, when Wubit got started with this presentation, it had like 80 slides or more. We're down to 40, okay? It will take about 50 minutes, and then we will go have some questions from the audience. The committee will hold the questions until we go into the closed session. So here, after several years, Wubit is here to defend his dissertation entitled Land Surface Phenologies and Seasonalities Using Cool Earthlight in the Temperate and Tropical Croplands. Plug that in. Here we go.
Okay. Yeah. Thank you, Jeff, for your introduction, and thank you so much for coming to my presentation. And I would like to thank also NASA Earth and Space Science Fellowship for funding my research. My advisory committee, Jeff, Mike, John, Gabriel, John, and Rex. for supporting me throughout my studies. And while we studied these two contrasting regions, Croplands, the temperate region and the tropical region, because the temperate region, Croplands or temperate region in general, is the most crop producing and exporting part of the world, while the tropical region is food insecure part of the world. So we need to see these contrasts to help food security issues. And also we use passive microwave data, and this data has some advantages, like it's sensitive for cloud cover, atmospheric effects, and other issues, even though it has some drawback. So we need to test or see these microwave M3 data, in particular its performance to track cropland dynamics. And here, food water security in East Africa. The tropical croplands have water intake, moisture intake limited. Particularly East Africa, we say that it's the most food insecure part of the world. The economy is dependent on the traditional rain-fed agriculture, and it makes it vulnerable to weather, extreme weather events like drought and floods. And also there is a mismatch between population growth and economic growth in this part of the world. And here, as the background, the picture shows a failed crop in Ethiopia during the 2015 severe drought, and this drought is the most severe in 30-50 years, even severe than the known famine in Ethiopia in 1984-85. This one is very severe. And about 20 million people were in need of food aid, which is 1/6 of the total population. And we can address food security issues or food insecurities through cropland dynamics studies, and these can be done using land surface phenology and land surface seasonality studies. When we say land surface phenology, we mean the timing and progression of the vegetative land surface dynamics as observed by remote sensing. Examples include NDVI, EVI dynamics. And land surface seasonality is timing and progression of the abiotic variables over the land surface as observed by again remote sensing. And examples include temperature and soil moisture dynamics. But these two terms, phenology, seasonality, are complementary aspects of ecosystem functioning because the one affects the other. And here I have 4 research questions that I try to address in this study. The first one is whether it's possible to use convex quadratic model, which are being used for optical data, to model M3 passive microwave data. So that's the first question. The second one is the synergistic use of the near visible near infrared mode is NDVI, and microwave M3 retrieved accumulated or integrated from the air temperature. So whether these combinations can be used to track cropland dynamics in the deep latitude. That's the second. And the third is comparing 2 phenomatics from different centers, different part of the electromagnetic spectrum, VOD from M3E data, vegetation optical data, peak height, and NUI peak vegetation greenness, whether these 2 peak heights can track cropland dynamics in the mid latitude again. So when you say VOD vegetation optical data, it's a microwave analog of NDVI, so that's a measure of the crop canopy, which responds to water content, vegetation water content. And finally, the fourth question is whether we can use, again, M3E passive microwave data in East Africa. Especially, it's a blended data set that we use for the fourth research question. M3E and M3. M3 is so the M3E is It's launched in 2002 and failed to function in 2011, but then M3 is a continuation of that. So it launched in 2012 and it's still functional. So here's the data set, and we are using that data to monitor cropland dynamics in East Africa. So the first three research questions span from 2003 to 2010, mainly using M3 data, but also other data sets in the optical region. And the fourth research question is using this M3E, M2 data sets, so 2003 to 2015, again with other data sets. So here, the M3E, the Advanced Microwave Scanning Radiometer, or EOS, alpha satellite. This data set is prepared by the Numerical Terradynamics Simulation Group at the University of Montana, in which Dr. John Kimball is FR. And this data set is twice daily, so nighttime, daytime acquisition, because it records the microwave emission, so it can function day and night. Therefore, it's twice daily. It has a 25 kilometer resolution, the robust data. And the data in this data set includes atmospheric still water vapor, surface air temperature, radiation chemical transmittance at 3 microwave frequencies. So these frequencies have the 3 here maybe wavelengths of about this dimension, and the other this one, maybe the other this one. So it's long wavelengths in general. And volumetric soil moisture and fractional open water elongation. These are the data sets that are included in the M3. And the other data set that I use is MODIS, particularly the Nubar MODIS reflectance data, which is a combined data from the Aquarius Terra satellites. And from this reflectance, I developed NDVI and EVI. And also I use land surface temperature from Mosaic and Terra for this study. And also I use meteorological station temperature and rainfall data to check our satellite data sets. And also TRIM rainfall data, 25 kilometer spatial resolution and daily data. And actual evapotranspiration from, again, simple surface energy balance model, which is developed by Dr. Gabriel Group. And this data has 1 kilometer spatial resolution and SFTN data. And to select the specific study sizes, I mainly use the IGDP MODIS global land cover, type 1% data, from 2002 to 2012. And from this data set, I developed I use land cover stability map or layer. And to do that, I assign the red color for the maximum percentage cropland over the study period, here the 8 years. The green color is assigned for the average percent cropland over the 8 years, and the blue color is assigned for the range of croplands again in this time period span. And the resulting layer here, this one is the crop stability map actually. Therefore, the yellow color here shows core stable area of a given land cover, cropland here. The white shows unstable core areas. The magenta displays unstable peripheral areas. So these are areas between two adjacent land covers. So there will be a change between these land covers. And the black shows non-existence of the given land cover over this given study period. I also use the USDA Foreign Agricultural Service crop map and Google images to help for the selection of the study cropland pixels. And finally, I have selected 163 M3 pixel sized cropland sizes for the analysis. So for all the research questions. And for the temperate region croplands, I use the data from DOTO 89, or generally approximately from April to October, and I will other data sets to avoid the frozen season. But for the tropical croplands, I use only the data for the 365 days data. And here, growing degree is defined as mean temperature increment about a certain threshold, temperature threshold. Here we use 0 degrees C as a base for crop growth. And the GDD is here calculated as the average of the daytime, nighttime acquisition data, the temperature data. So so if this value goes below 0, we use 0 because it's our threshold. And the accumulated growing degree day here is the simple accumulation of the growing degree day over the study period. And the VOD is also calculated using this minus ln of TC. The M3 data set has vegetation transparency, and therefore it's turned into VOD with this formula. And for some of the data, growing degree day basis of calculated NDI, ETA, and crystalline water vapor, I fitted convex quadratic model for this data as a function of accumulated growing degree day for the temperate croplands, and as a function of accumulated crystalline water vapor days for the tropical croplands, and also actually here the accumulated ET. So here, from this convex quadratic model, I have derived two phenometrics. The first one is peak height of the given variable, so using the coefficients of the model, and also time to peak. So it can be thermal time to peak. So here, for example, here, accumulated growing degree day during the peak temperature, we can take DDT or other variables. So thermal time to peak, the moisture time to peak, or thermal time to peak was also calculated. So when we come back to the first research question, that's about the using of this convex quadratic model on M3E data, passive microwave data. And the paper for this research question was published in 2013 on the Environmental Research Letters Journal. And the specific study titles for the first research question include about 4 sites in North Dakota, about 5 sites in the Canadian prairie, and about 4 sites in the Volga River basin in Russia. And here, the convex quadratic model fits for the growing degree day. So this one is M3E data, growing degree day. So we have got a nice fit with this model. With R square of greater than 0.9 for all our study cycles. And this one is the land surface phenologies of vegetation optical layers. So the vegetation optical layers for the North American study cycles and vegetation optical layers for the Russia cycles, Cropland cycles. And here, the North American study cycles have higher dynamic range of VOD and also high peak compared to that of the Russian cropland cycles. And the peak for the North American cycles is achieved around 2000 accumulated growing degree day, or about early August. But the peak for the Russian cropland cycles is about mid-June, or about 1000 accumulated growing degree day. And the reason for that is these North American cycles are the spring wheat producing belts. So these are spring wheats, therefore they mature later than this one. This is the winter grain producing site of Russia, and therefore crops mature early. And they have about a 2-month difference. The peaks have 2 months difference. And we also fitted this VOD with a convex quadratic model. But as you see here, the core growing season shape for the VOD is different than a convex quadratic model fit. And therefore we decided to fit only the core growing season. And therefore the core growing season is fitted a nice layer value. And the other point here is, so this is the 18 gigahertz vegetation optical lasers, while the lower one is the 10 gigahertz VOD. And that's, so the shorter wavelength, which is the 18 gigahertz frequency, has higher VOD than the longer, the shorter wavelength, the longer wavelength, the 10 gigahertz. We are going to see the 6.9 gigahertz radiation optical depths because this diode is produced in 3 microwave frequencies. There are lots of gaps for the 6.9 gigahertz, likely or maybe due to radio frequency interference. And for the first research question, yes, we can fit Cornish quadratic model for a microwave data set, but it's partial because the cold growing season-based optical depths, the shape is a bit different than the Cornish quadratic model, and therefore it's partially yes. The second research question about the synergistic use of MODIS and DBI and microwave M3E air temperature accumulated corrective reading. And the paper for this is published this year at the Remote Sensing Journal. And the specific study sites for the second research question are in northern Russia, particularly Ukraine, southern Russia, and northern Kazakhstan Cropland sites. And using the method that we see before, I selected about 49 study pixels. And here is the Cornish quadratic model fit again for the grain degree. And here I have 2 data sets from MODIS, land surface temperature, and from M3E air temperature, growing degree. So both growing degree track similar seasonal pattern. That's one. And second, both can be fitted with this quadratic model nicely. But when you closely see the model fit, the M3 data has a bit superiority compared to that of the MODIS land surface temperature growing degree. And actually, there is also another point that the observed growing degree here is a bit lower or inferior compared to the model fit. And we will come by after some slides why that happens. And here is the NDVI, EVI as a function of M3E air temperature accumulated growing degree. So optical data and microwave data. And for about 4 sites here that are presented. So number 4 here is presented, the second one here, number 1 the first here, and this one here, and the last one here on the top. So for the first 2 study sites, 1,000 study sites, these sites actually is 2003 data, 1-year data, because this bimodality, unimodality, if it's averaged over time, it will not clearly from this bimodality, unimodality, and therefore 1-year data for this one. For the others, it's averaged. So the southern study sites support 2 growing seasons. So winter grain and spring grain. But when you go up to north, it has only one seasonality. But when you go again up to north, northern area, we have again a unimodal seasonal pattern. But the northern study sites have a shorter summer growing season, and therefore they have narrow data here. And this is internal seasonality or internal variability of again the radiation indices. So this is for a single site at the southern part of Ukraine, and from 2003 to 2010. In 2003 and 2004, these sites had 2 growing seasons, but then from 2005 to 2009, these sites have a single growing season, and then in 2010 it comes back to again double growing season. So winter grayness, summer, winter, and spring, winter grayness. So based on this dynamics or variability of specific cycles, I grouped all the cycles into 3. The first one, cycles that didn't show any change over the study period, and these are found in the northern parts of our study cycles. And cycles that support, that showed one change over the study period, over the 8-year study period, and these are cycles found here, and sometimes we have bimodal, unimodal first, and then changing it to bimodal seasonality and the reverse. And sometimes on the southern study cycles show two changes over the study period. So they were unimodal and then changed into bimodal and unimodal and vice versa. So this is a general grouping of the cycles. And the reason for this may be the following period difference, crop failure, and other factors. And we didn't go further to investigate why that happened. And this one is the grain degraded residual with basic optical, especially NDI actually here. So this residual comes from the grain degraded and the model field. I mean, the observed grain degraded and the model field different. Therefore, here, when the vegetation is peaking here, we have a negative residual due to evaporative cooling. So the model is superior than the observed grain degraded, because observed grain degraded is lower due to evaporative cooling of the vegetation here. But at the beginning and end of the growing season, the residual is positive because the sensible heat flux was superior or greater than the latent heat flux during this period. And to conclude reserve question number 2, yes, we can synergistically use the optical model NDI with M3 air temperature accumulated grain division to characterize croplands. Because we were able to differentiate between spring and winter grains by combining these two data sets, that's one. And also the M3 air temperature grain degrade showed a superiority in terms of product models over the models than surface temperature grain degrade. And also the M3 grain degrade residuals were able to manifest the evaporative cooling effect of the growing season, the peak, especially the peak growing season. And here is the third research question about the comparability of microwave vegetation optical data's peak height and the optical NDVI peak greenness period, whether these two phenomena track cropland dynamics in a similar way. And the paper for this research question is already under review at the Chemosensing journal. And here is the result. So vegetation optical data at 3 microwave frequencies and NDVI for 3 sizes here. So the lower side, especially if you see the southern side, the study side at the bottom here, this side supports down growing season in 2003, 2004, and also in 2010. So the vegetation optical data at all the frequencies responds or track similar seasonal pattern to the NDVI. So this VOD track similar seasonal pattern compared to the NDVI. And here is the peak height for the VOD, the blue one, and the NDVI, and the VOD peak height at 3 microwave frequencies. The NDVI peak height was determined using convex quadratic model fit. We fit the NDVI with this model and then derive the peak height. But for the VOD, since the fall growing season shape is not suitable for this model, I picked the seasonal maximum as peak height. And when I compare these two heights, there is a lag of 1 to 2 weeks. The VOD lags the NDVI by about 1 to 2 weeks. And that's because the NDVI is sensitive for vegetation greenness or for the active radiation absorption. But the VOD is sensitive for above ground biomass and canopy water content. So the greenness comes first than the water content and the biomass, the peak biomass. And here is the regression, linear regression fit for the peak height VOD for all our study sizes as a function of peak height and NDVI height. And they are fitted nicely. But when you see closely, the 10.7 gigahertz vegetation optical data show a little bit superiority than the two microwave frequencies, but this difference is not that significant statistically. So to conclude the third research question about the comparability of the VOD peak height and the NDVI peak greenness, our answer is yes. These two phenometrics can track similar seasonal patterns. The first time series of the VODs at 3 microwave frequencies were able to track similar seasonal pattern to that of the NDVI, including both the bimodal and unimodal seasonal patterns. And second, microwave, microwave peak height VOD favorably corresponded with the peak height NDVI, but there's a lag of about 1 to 2 weeks, and this is because, as I said before, canopy water content, background biomass peak is later than the peak greenness. But more research is needed on how best to use this complementarity between the two data sets. And research question number 4, whether we can use the M3 passive microwave data in East Africa, in East African croplands. So current approach that usually the temperate croplands be adapted to the cloud obscure and data scarce part of the world. That's the question. And the research, the paper for this question will be submitted in early February this year. And these are specific study sites for the East African cropland sites, especially in Ethiopia, South Sudan, and Tanzania. Ethiopia and Tanzania are the major grain producing countries in that region in East Africa, but South Sudan is the newest country in the world, so we need to see cropland dynamics in these countries. And we use, as I said before, about 13 years of data using the blended M3E and M2 data sets. And I heavily use actually the Google Earth images to select the croplands in addition to the knowledge that covered. And there are 5 because there is high range or variability of this cropland percent coverage in the knowledge data set in this part of the world. And I selected about 100 specific citizens or study sites, and most of them are actually in Ethiopia. And that's for a purpose for further analysis. I have here a complicated graph of the Antarctic Phenologies, Seasonalities. Here, this color shows the vegetation optical depths, and the red color here, gray degree day, and this one, pristine water vapor, and the gray color here, volumetric soil moisture, and this blue color fractional water, and the light blue bars are rainfall from stream data. The other data are from M3E data, the blended data, but the blue color, the blue bars are from stream rainfall data. Since the system is moisture limited, the other variables as you see here are driven by the rainfall. So they are peaking the fractional water, soil moisture, the crocus, they are peaking during the peak rainfall season. And if you see here also in Tanzania, so in Tanzania you can get double growing season. They have short rainy season and long rainy season. And the M3 variables we are able to track this bimodality, similar to that of the stream rainfall data. And here in South Sudan, a similar thing, but this side is a lowland cropland set, and it has a higher dynamic range, seasonal dynamic range of precipitable water vapor. And the Ethiopian site is a highland humid site, and therefore it has higher vegetation optical depths, high fractional water, high volumetric soil moisture, and also very high rainfall. Here the scales are different, 120, but here it is almost double compared to that of the South Sudan. And here we see also our variables with a convex parallel model. Here is particularly the actual vapor transpiration from a different undisputed data set. And this one is the pristine water vapor. And these two sites, these two are from Ethiopia. single site in Ethiopia for the two areas, and this one is in Tanzania. So Tanzania is the biomodal seasonality. And so the actual evapotranspiration track in a nice way is bimodal rainfall pattern. Also the pristine water vapor, but the actual evapotranspiration is very sensitive for the rainfall compared to the pristine water vapor. And here is the linkage of crop production with land surface phenology and seasonality. So for this linkage, I use the notion that crop evapotranspiration is proportional to crop production and yield data. And for that, I use the actual evapotranspiration data. I also use the vegetation optical dial difference. The daytime dial difference minus the nighttime, or the descending part, minus the daytime vegetation optical difference. So here is the purple color. This one is the vegetation optical dial difference, nighttime minus the daytime. And you can when the vegetation is actively growing due to evapotranspiration. So the daytime is lower, and therefore it has high dial difference. And to calculate area, so area under curve of this DOD dial difference, I use this gray color volumetric soil moisture to determine the cut points. First, this volumetric soil moisture rises up when rainfall starts, or the rainy season starts, and then it goes up during the peak rainfall season, but comes down here because the microwave emission is attenuated by actively growing vegetation. So therefore, it comes, this soil moisture comes down before the rain is going. And then this soil moisture comes up, even though the rainfall is going down or drying out. But since the vegetation is drying out, the soil is exposed, and therefore the emission is recurrent, and therefore it's picking up. And I use these two cut points, the start of rainfall season and dry period of the vegetation, to calculate the area under this curve. And I use similar methodology for the ETA curve also. And here is the relationship between AUC for the ODDD and crop production. And this is for production, this is for yield data. It's for some kind of relation, because it's not that perfect, but it has some kind of relation. And this crop production data is at a Woreda level data or district level data. We call it Woreda language, so district level data. And one district is about 1 to 2 MCE pixels. So the MCE pixel size, even though it doesn't, it's not a problem for the analysis because the crop production data is already coarse resolution data, and therefore, so this data is gained through personal communication. And I have also another relationship. It is again the ODDD, AUC. So this orange color. So in time, from 2002 to 2010, 8 years of data, and it doesn't show significant change. The land surface phenology or this phenometric doesn't show significant change. And also this is the rainfall data, annual total rainfall over these study periods, 2002 to 2010. And the rainfall is not also showing any significant change over the study period. But this is a production data, for production data, that's officially reported by the federal government of Ethiopia. And this data showed over these 8 years a tremendous increase. It increased, I mean, it's doubled within just 8 years. And the annual increase in production is 6.5% per year. So it's a tremendous increase. And here our data sets didn't show any change, but the production showed a tremendous change. And if we regress this data with production, it doesn't show any relationship. And the point is this data set, the federal government data set, is also officially reported to FAO and other international organizations. And usually, the country's development is, I think, calculated from such kinds of data. And so here, the federal government data is increasing very, in a high way. But here, actually, this is 1 year data. We can't compare it with that. Since the system is driven by rainfall in that part of the world, without this significant change, the production is increasing, and that has to be judged. And the production data is small for artisan agriculture, it's not mechanized, no agricultural inputs. So this comes from 4 plants. So the data has to stand down. So to conclude this question, yes, we can use M3 EPAT microwave data to characterize cropland dynamics in East Africa. So yeah, we can track Java growing season, in the growing season, and others. And the seasonality of the M3 data was comparable with the independent stream data set, and also the other independent evapotranspiration data sets. But the linkage with crop production is uncertain, especially with the officially reported crop production data set, and therefore lower administrative level crop production data or independent data crop production data sets is needed to check the linkage of these M3 data sets with crop production data. And here's the final point about comparison of thermal and moisture limitation in the 2 different parts of our cropland study cycle. The blue color is for a Russian cropland site, and here the reddish color is for Ethiopian cropland site. And here is crystal water vapor as a function of growing degree data. And when you see the Ethiopian as the reddish color, the growing degree data doesn't show any significant, any large change or seasonal dynamics in terms of growing degree data. But seasonal dynamics of the pristine water vapor is high. So it is a moisture limiter system. But for the Russian side, the growing degree data has a larger dynamic range compared to that of the pristine water vapor. So that's a kind of comparison. And finally, I am interested to apply, to use SMAP data as soil moisture active passive products. Again, to compare that with, to study cropland dynamics, this is data actually is coarse, but it's a longer wavelength, and therefore we may get some good data because the OD, soil moisture, and temperature data sets. So I need to access that for cropland dynamics or seasonality. And it's also interested to work on models about anything else. I can link that with the crop production data. And that's all. Thank you. And questions?
Okay, you'll take some questions. Wilbert, remember to repeat the questions for the audience in the cloud.
Okay.
Mark, you show how all these methods apply in crops and croplands. Do they also apply in natural systems, or which ones would they, like forest versus non-forest?
Yeah, so it's about the applicability of this data for the different land use systems. Yeah, we use it for croplands actually, but there are other researches out there for other land cover systems too. So in general, I think in forest systems, in the boreal system also, and there are also other products, freeze-thaw seasonality, and yeah, they are usable. They are used for various purposes. It is where places here for croplands only.
David.
I thought you were going to be talking about something interesting about agriculture. You've done curve fitting to essentially the easiest agricultural classes you can fit to, right? The reality is, and that's not necessarily a problem because you say in the thesis that it's mid-temperate, temperate latitudes, right? But the world, the majority of the world's agriculture, if you look at an NPVI profile, what does it look like? Does it look like the kind of nice profile that you get?
Yeah, in Croplands, more or less, yes. It can be fitted with models.
Well, if you look at, for example, rice in Southeast Asia, you get 2 or 3 crops a year, so you get 2 or 3 picks. Even in the United States, there are crops that have 2 double cropping.
Yeah,
2 picks a year,
yeah.
right? And then harvesting, when crop growers are putting in a new crop rotation, crop intermixing, all of these things give you very different profiles than what you showed. And so I would suggest that in your future work, when you talk about future work, you talk about that. Because essentially you fit curves to the easiest kind of crop you can fit to. I think that's a fair statement, but if you want to disagree, please do.
Sorry? Just the last one? Sorry.
Well, I talked about it. I mean, is what I just said a fair statement?
I think I missed the last one.
Well,
so maybe
what he's saying is that he wanted to see some instances of you fitting the double peak stuff in there, and those were in some of the 40 slides that I had him remove.
Yeah. Sorry. So in our case we have got two peaks, winter, spring grids, and we fitted those separately. I think as I showed that on the ETA curve, we did that for the NDVI too, and also we were able to see even in those 2 seasonalities. Sometimes at the end we get the winter crops emergence, so a kind of small peak. We fit those 2 curves on the NDVI too.
Any other questions? Yes, David. Follow-up question.
You have 4 questions. Usually a good PhD has 4 hypotheses on your questions, but we'll let that go. I would argue that you can answer yes to all your questions before you even started your PhD. The question is how well you can do those things, not yes or no. So all your 4 questions, couldn't you argue just say, well, the answer is before you even started this PhD, you knew the answer was yes, because you can fit curves to just about anything, right? So the question is how well, not can you, I would have thought. And that goes to any PhD thesis, really. It's just saying, can you fit these curves, right? Can you do this? The answer is no, yes you can. How well can you do it? So in having done all this work, how well do you think you did? In other words, overall, in a couple of sentences, what worked and what didn't, and how well, not just a binary yes, no.
Yeah, so the point here is we are using heavily the pattern microwave data. Usually, land-surface phenology seasonality is studied for many years using optical data, not much on the microwave data. Actually, there are, but not much. So our interest is to use this microwave data, how it performs in terms of cropland land-surface phenology and seasonality. And then we started our study in the temperate croplands because they are well-studied croplands. So we have enough literature. So we are trying to distinguish this data, the methods in the temperate croplands, and our intention is to gain knowledge of our meta data and other status in this temperate part of the world, and move this out to the tropical croplands, in which not much study on that part of, not much literature on that part of the world, especially the optical data is much affected compared to the temperate regions by cloud cover, aerosol, and other effects. So actually the Croplands over there in East Africa are very fragmented, which may not be suitable for the passive microwave data. But knowing that drawback, we assume that we may get advantage of this this atmospheric insensitivity and other status of the microwave data to apply it in East Africa. And then the final point was if we model croplands in East Africa, we can use that to link with the crop production data because that part of the world is the most province secure part of the world. And if we can model the croplands, then we may link that with crop production data. That was the total story. But due to a lack of quality crop production data, as you saw that on the first research question, our effort is not as we want, because these cropland production data sets are usually manipulated for the crop production data is manipulated for political purposes, and therefore they are increasing from year to year without that was not manifested using this M3E data sets. But the intention is so to gain knowledge from this temperate part of the world and then apply that in East Africa and linking that with crop production. And these kinds of examples using optical data are actually done by, so for example, CHEOSNet, the USGS, with USID, so the crop early warning system thing, using Moody's NDVI data. So we, our interest is to do that kind of thing with microwave M3E data or microwave data in general. That's the whole point.
It's 4 o'clock. You can get a chocolate chip cookie on your way out, unless someone has a dime with a Christian, and the committee can convene to 103. Thank you.